means. Now, theoretically, LDA is also the best tool available for dimensionality reduction. There isn't something which is, in my terms, better than that. Now, I must admit that nobody really uses LDA. So what I'm gonna do is, apart from giving you the theoretical background of LDA with some equations this time, I'll also be talking about the engineering side of LDA. That I mean, what's the practicality of the method, and I will try to really make it a case for the fact that it is, in my opinion, the best method possible for dimensionality reduction. So I don't know anything that does it better. But then I'll also talk about practically why is PCA still the de facto choice and LDA being better than PCA. Why don't people that actively use it? So you'll keep getting my personal flavors, of course, from a very standard lecture on LDA. But then um, task over here is also extremely simple because two of the background materials that are needed for this thing, the linear discriminant analysis, have already been covered. So it's like 95% of my topic is already over. That leaves me with enough time to give some musings. So you have dealt with PCA and all the mathematical background behind the PCA. The LDA is just a slight variation over the PCA, and of course, you have also been through SVD, a very fundamentally used tool. So you understand dimensionality reduction by every means possible. So just to repeat for the people, in my own terms, from an engineering or application side only, what is PCA? A lot of people would say that it's really a two-dimensional data where this is my feature one and this is what is my feature two. But then, of course, a lot of you might agree with me to say that the two features are highly correlated. It could be anti-correlated as well. So when the first feature increases, the second feature also increases. It doesn't always happen like, I mean, if I take this one and this one, the first feature increases, the second feature, instead of a small, has a large increase. So there might be exceptional cases, but overall, the two features are extremely correlated, and therefore, if I only take the first feature, if I only take a linear combination of the feature which is given by this line, I am doing good. I am mostly doing all the problems that I need is solved because my loss in information is only these perpendicular lines that you see. So, and the perpendicular distances are very small. That's the information that I have lost. So, if I change the coordinate axis system, instead of this coordinate axis system, I take in a second coordinate axis system where this is f1 dash and this is f2 dash. There is no loss of information because I'm just rotating the data, as we call it. You can always transform the data as you like. The information is not lost over there. But thereafter, I say that if I delete f2 and project all this data on F1 only. So basically, I had a XY. I'm not considering Y value, I'm only considering X axis value. So this is the only thing that I can see. I will get in this kind of a distribution. So this data is here, this data is here, and so on and so forth. And you see that the loss of information is minimum. This information has been lost, and therefore I say that the data is really one dimensional in nature, and PCA does that beautifully. The PCA absolutely wonderfully does that. But then that's from a theoretical point of view. I come to a little bit what I call as the more practical point of view. And I mean, practically, I have too many questions around over there, and let's answer them one by one. PCA and LDA are also the most abused tool that I find in research. So people just want to use it. There may be no case, there may be no application. People just want to use it because some nasty supervisor, some nasty editor, some nasty reviewer is asking questions that how did you try to change the state of the art, and one of the standard ways to change things is to apply PCA to mortality reduction and say that that's a novel contribution. So let's answer some of the obvious questions one by one. Now, first of all, no real data looks like this. So it's a blackboard data. In real life, whenever I would identify two features, let us say to find out whether the faces of this thing, mine or the faces yours, I identify features like the distance between the eyes and circumference of the face and stuff like that. If I say that two features are correlated, they are highly correlated, I would not pick them at the first place. So no real data really looks like that. In reality, the data is a lot more clumsy in high dimensional spaces. So what dimensionality reduction does is that dimensionality reduction says that we know that there will be a loss of information. There's nothing denying the fact that there will not be any loss of information. Of course, there will be a tremendous loss of information, but what we are trying to do is that when we're trying to minimize the loss of information and trying to maximize the information content, that is what is called as dimensionality reduction. And I mean, that's exactly where it is different from something like zip compression that you have. There is no loss of information. So if you zip a file and you unzip up, you get exactly the same files. That is how it is different from, let's say, a JPEG compression, because a JPEG compression, of course, the original image and the JPEG compressed image are well, associated with the loss of information, but the loss of information is too small and sometimes not even visually visible. So here there could be, depending upon the problem, a small to large loss of information. But then, if I do have a small to large loss of information, it's important to understand and discuss why should I use dimensionality reduction today. Now, one of the standard answers that a lot of students give is the answer which was absolutely valid when the textbooks were being written in the 1980s and the 1990s. So, in the 1980s and the 1990s, if you belong to that era, you would know that we had very small amount of data for every problem. So those were the cases where the textual data was very small, the photographic data was very small, the biomedical data was very small because every data had to be captured using significant efforts. So all the data recording people of that time tell us about how painful was it to record one segment of data. Digitalization was almost negligible. Yes, the computers did exist, but most of the hospital records were still papers. Most of the book records were physical books being printed and stuff like that. Nobody posted pictures on social media in the 1980s and the 1990s. So at that time it made a lot of sense to say that I have a data which has a large number of features, and what I do with that is that I also have a small amount of data because every data item at that time needed a lot of efforts. So I have a data table which looks like this. This is very large, which is my number of features, and my number of samples are actually small. So what do? I do a dimensionality reduction. I get a data table which is smaller over here, and of course, it continues to remain small over here. And that's what I give to my machine learning model. So the only thing that changes is this becomes small. This would remain to be small itself, and then I apply a machine learning problem. The other problem around the 1980s and the 90s was possibly some of you may have faced that as well, that the computing resources were very slow. So to train models, you would have to give in too much amount of time. Of course, there were no GPUs, so there was no parallel processing. In fact, there were no multi-cores as well. So that era happened a lot late. So this all made absolute a lot of sense that I want to reduce the training time, and I want to make the problem easier to learn. And therefore, you'd say that I'll apply this technique that's called as dimensionality reduction. What it would do is that my training time would get absolutely significantly reduced. Some people say that if I have 50 features versus I have 25 features, the training time would get reduced by half. Theoretically, it follows the curse of dimensionality where the complexities could be theoretically exponential. Practically, of course, it is not exponential. That's because of the hyper redundancy of features. So I could significantly reduce the computation time if I do dimensionality reduction, as well as the fact that I have a problem where my data is small, so I cannot regress large models over small pieces of data. I would undergo what is called as overfitting. I didn't check the schedule if the overfitting lecture has already taken place, but then, like everybody, I'll keep giving reference to overfitting. And therefore, what I really need to do is that I cannot afford a large complexity model to avoid overfitting. I need to take a small complexity model. And the only way to do that is to do dimensionality reduction, is to make the overall problem easier. So things like PCA, which we discussed over here, they are statistical tools. They are extremely stable. They only apply correlation statistical properties, and they are extremely helpful in dimensionality reduction. So this is a very standard answer that probably a student would give you. We have a problem when we come to the modern days. See, every domain, the data is increasing like hell. So I gave you an example. We wanted to record some trajectory data. We just set up a camera outside, and at least in an unsupervised sense, we recorded like a humongous amount of data. So that's not, data is not really a problem. These days, data could be generated by generative AI systems. You could just ask ChatGPT to generate synthetic data. That's still good enough. You have excellent simulators that could generate realistic data. For medical, we have medical simulators. For robotics, we have robotic simulator. There are tons of photos and images and everything available on the web. So probably my this is the number of samples is increasing, and because the number of samples is increasing, so I can train large models. I have clusters and GPUs to train large models in parallel. I have a lot of compute available at my fingertips these days. So the relevance has become, the classic answer is now something to really look into again. I'll give you my own views on that. And that's actually one of the embarrassing stories. So one of my own students presenting the post-graduation thesis kept saying that we want to reduce dimensionality, data is scarce, compute is scarce, and then the external is like, I see that you have too many computer systems, your training time doesn't appear to be that much, you could have trained for days together, and why is data small? So you're doing something like object recognition where object is in front of you. So take a camera and keep on making a video recording the object from multiple angles. You'll get 30 frames per second. So there's no dearth shortage of data in practicality for you. That's what a lot of us deal with these days, that it's becoming impossible to justify some things which was completely justified in the past. Now, I will answer that question later on as well, but I will give you the short little answer that uh, techniques like the PCA and techniques like the LDA is just a small bit of the PCA, are still extremely useful for reasons wherein I'm dealing with data of, let's say, a very rare disease, and every subject is by 1 unit of data. So I need to find out everything that I could do in order to reduce the dimensionality, because my data actually becomes very small. Those problems still exist. A little bit more practically is what I'll talk about later on as well, that I want to visualize a high dimensional data. How do I do that? So I want to plot a high dimensional data. And there's, as you know, no way that I can plot a 5 or 6 dimensional data, because human eyes have the limitation. The human eyes can only see 3D, and my screens are 2D, in which I can get a 3D effect. So in any case, I cannot plot a dimensional data. So, and these days you need a lot of plotting. I mean, if you have a deep neural network, you need to plot the original data after layer one, after layer two. You want to see what's happening. So, if I need to visualize data, I will have to reduce it to 3 dimensional, and that's one of the standard use cases which still exists. So, practically, a lot of PCA, a lot of LDA is being used for visualization, where you want to look at data at multiple stages. So you can only plot 3D. So whatever be the dimensionality of the data after first layer of the neural network, after second layer of the neural network, after first layer of the decision tree, after second layer of the decision tree, and so on and so forth, you just cast it into 3D and plot a 3D. And of course, they make an interesting publications. From the classic point of view, of course, I'm only dealing with problems where, I mean, I cannot casually say that I have problems of compute these days. You can train models for days. I cannot say that I have problems of small data size these days. You can record a lot of data. But then, if any one of these problems really do exist, these still make an interesting case. Now, the debate that also may have been covered, I'll take this one as well. That suppose I want to do dimensionality reduction, what method would I really use? Would I use something like a PCA, which is a filter method, or I will use something which is called as a wrapper method? Before I give in my own musings about the filter and the wrapper method, and why filter methods are more practically realistic these days, the 1980s and the 1990s textbooks are too old to be considered I mean, practical these days. But then, I mean, let me just repeat what people would have talked about earlier, that what are these two class of methods, the filter and the wrapper methods. So, one of the ways to do dimensionality reduction is that I have a high dimensional data. I pass it to a statistical technique. The statistical technique uses statistical properties, and it gives me a low dimensional data. These are the approaches. You have the PCA, the SVT, and now the LDA, which does that. But then the problem with these approaches is that suppose I select modified features F1 dash, F3 dash, and F9 dash, and I had 5 classes A, B, C, D, E. Now, if I have to select a new feature, what the statistical techniques would do is they would globally try to maximize the distance between the classes A, B, C, D, E, or they would like to maximize the variance between all the data taken together. But what happens is, after taking F1, F3, F9, I see that all the classes are very well separated, but C and D are being confused with each other. To give you a practical example, So let's say I have Shah Rukh Khan, Narendra Modi, Rahul Kala, Ranbir Kapoor, and after taking the top three features of PCA, I see Narendra Modi looks very different from Ranbir Kapoor, and Shah Rukh Khan looks very different to Narendra Modi, but Rahul Khan and Shah Rukh Khan look very much alike. I keep praising myself like that. So now what I want to the new feature is I only want to maximize the separation between Rahul Kala and Shah Rukh Khan because the other three features are anyways doing a good job in separating between all the other classes. So my new feature should only try to maximize separation between these classes, and none of the statistical techniques they actually do that. So in the wrapper approaches, what we do is we take a machine learning model which does the entire classification, and we use an algorithm to select feature subset. We use another machine learning algorithm to select the subset of features. You could use genetic algorithm to do that. You could use trial and error to do that. You could use local search to do that. And you are trying, I mean, so machine learning model is what you are taking it as a black box, and the subset selection problem is the one that you are solving. So machine learning is like taken as a black box. Given the data, machine learning will be able to give you an accuracy. I solved the subset selection problem, the feature selection problem. This is the problem that I solve. I could use optimization, I could use genetic algorithm, I could use local search, I could use theoretically exhaustive search, but that will not work. And that does a much better job than filter based techniques, because the filter based technique they do not consider this problem that only my Rahul Kala and Shah Rukh Khan faces were getting confused with each other. So I need features which maximize distance between Rahul Kala and Shah Rukh Khan and nothing else. So they look at the entire data globally. They are statistical techniques. uh, there are two problems with wrapper-based approaches. So practically, they are only used in publications. You will never see a real industrial use case, a real application where we use a wrapper-based approach, because I mean they don't do the things which statistical techniques do. That is to take the combination, linear combination of features or correlation between features as a direct metric. But then the major problem becomes in the wrapper based approaches is that they are extremely slow. So, oops. So the entire problem becomes with this approaches is that the wrapper-based approaches are the ones which will be extremely slow, and they are slow because number one, that if you're doing it like a genetic algorithm, every fitness function call is trying to find out what the best features subset is, and it takes in a huge amount of time. Unfortunately, this next lecture is not on what I would like to, I mean, what I wanted to discuss, which is the filter and the wrapper based approaches. And that makes it extremely slow. And the chances that a few selected features out of a big number of features are actually making a good machine learning model is extremely small. So when I talk about dimensionality reduction, I don't want to do what the students do, that they would have 20 features and they'll make it 18 or 17, just lose three dimensions. You might have eventually not used at all and got a better performance. I'd like to go from 10,000 to a few hundreds, or I would like to go from thousands to a hundred. So 10 times or 20 times or 50 times the dimensionality reduction. That means most of the features are lost. And for that, filter-based approaches turn out to be much better. So the wrapper-based approach have the curse of dimensionality. So it's an exponentially slower problem to solve. And practically, when you need to do a very large dimensionality reduction, you cannot go with the curse of dimensionality technique. You have to go with the filter-based approach, which is statistical. So it is extremely fast. But I will be taking my closing remarks on the same thing, speaking about the practicality of dimensionality reduction in the modern day systems where compute data is not a problem and the de facto solutions are all deep learning based. But then before that, let's touch upon the hardcore problem which I have been called for, and that is the problem of linear discriminant analysis. Now, because the only thing that I need to do is to change PCA a little bit, and everything will remain as it is of the PCA. So let me tell you only the differences that are involved from the PCA, assuming, of course, that there was a wonderful lecture I heard of the PCA. So the PCA part is something that is now known to all of you. So I've got exactly the same data as before. So this looks exactly the same data. The only difference that happens is that I have my classes. So this is my class 2 and this is my class 1, and everything else remained the same. Now, if I was a PCA, I would have maximized the variance. That's what PCA does, to select axes which maximize variance over all data. So, but I have an extra information, and that extra information are these class labels. So, can I adapt my PCA technique to also make use of the fact that I have the class labels? Can I use the class labels in my decision making? Can I somehow get help of these class labels and do something about it? And that's exactly what my aim would be. So, informally speaking, LDA is sometimes what is called as the labeled PCA. So, PCA, which also has the label information, or it is also sometimes called as the supervised PCA. A PCA, the principal component analysis, in which I have these class labels as an additional information. So conceptually, I will end it up in like 2 slides. I will tell you how are these class labels theoretically being injected into the PCA algorithm, and then in terms of the working of the PCA algorithm, which you have looked at already, I'll say which exact line needs to change. It's simple because only the input to PCA will change. So in the PCA, we were calculating the variance of the entire data set global. The one difference that you see is I only calculate the variance of the data separate for each classes. So I have class A and class B. I separately calculate the variance of the first class and I separately calculate the variance of the second class. Now, typically in PCA, what you do is you maximize the variance of the entire class, but then we know from the lecture of k-means clustering as well as from the other lectures in machine learning that I need to minimize the what is called as the intra-class variance. So now you see that this is one of the major objective. Instead of maximizing variance, I'm actually minimizing variance. So I want to select a coordinate axis system wherein all the data in the projected coordinate axis system lies as one small cluster. It lies as one small cluster, and therefore I say that I want to minimize the intra-class variation, while a normal PCA does exactly the opposite, as maximizes that. However, when it comes to between class or when it comes to inter-class, so that's the mean of the first data and this is the mean of the second data, I want to maximize the inter-class separation. So I want my classes to be as far apart from each other as possible. I want all my classes to be far away from each other as possible. And because I want my classes to be as far from each other as possible, I want to maximize interclass separation. That is what my aim is going to be. So this is the interclass distance. It's a distance between the two classes. I want to project the data in a space where this distance is maximized. So I will select a new coordinate axis system. I will select a coordinate axis system which is a rotated version of the coordinate axis system, that's PCA. But my objective will be different. I want to maximize the interclass distance. That means I can rotate it by some means such that this distance appears to be very large, I would be more than happy to take it. So let's say out of F1 and F2, in terms of interclass distance, which is the best feature, so, in terms of interclass distance, this separation is a very small separation, but this separation is a very large separation. So, F1 is definitely better than F2 in terms of interclass distance. But what if I, instead of F1 and F2, I take F1 dash, F2 dash, F3 dash, out of all these rotated coordinate axis system, which maximizes the interclass distance? And I mean, as it appears to me that this axis is probably good because the interclass distance is what is maximum between them. But then that's not the only objective. What I want to do is I want to minimize these variations as well. I want to minimize the variation between the intra-class distance, so that's between the data of the same class. I want to minimize this distance. From which view do I look at these classes such that the variance appears to be very small? In terms of F1, it appears to be now, I mean, of course, we need to take a standard deviation. There's a difference between minima and maxima, which is not the standard deviation, and we need to take the standard deviation. So it appears F2 is really slightly better than F1 because the variance is small of the intra-class distance. And similarly for the other one, remember that I informally plotted the difference between the maximum and the minimum. You will of course use the standard deviation or in higher dimensional spaces, the covariance matrix to calculate this thing. So overall, I need to minimize the intra-class distance. Uh, so my objectives are clear now. So that's the only thing that I need to do. I want to do a PCA, but my objective instead of variance maximization happens to be maximizing the distance between the classes and minimizing the variance between the data of the same class. And mathematically, it is very simple for me to do that. So uh, the mathematics is the easiest that you would actually think of. So I have a problem. Let's say this is the class number one, all the data of class number one. This is A, this is B, this is C, this is D, and this is E. So A is some vector. Currently it's F1 and F2. So it will be a 2 cross 1 vector. And similarly for B as another 2 cross 1 vector, and for C, D, and E. So what I will do is I'll say the mean of class number one is equal to A plus B plus C plus all the way up to E divided by 5. So I get this thing as a d cross 1 vector because each one of the data is d-dimensional in nature. Now, a lot of people initially into computing ask, why do we always take the column matrix? Why not we take in the row vector? God knows who decided the convention that data always has to be a column vector, not a row vector. I'm still trying to find somebody who made our life terrible. So I follow convention, so I always take it as a row vector. But then if you're doing machine learning using open tools like TensorFlow, you would know that they have already changed that notion where all the data are row vectors and not column vectors. This is theoretical, so I took it as a column vector. So F1 and F2 was like this, and not what you would normally do like this in programming. So I have my mean of the data. So I have this mean that I showed around over here. What I also need to measure is the variance over here. Now, currently it appeared that variance was just a standard deviation sigma, which is I was to prepare a result today, and everybody who knows how results are prepared, so you calculate standard deviations of the batch, and then you say 1 sigma average plus minus 1 sigma are average students, average plus 2 sigma are good students, average minus sigma are bad student, average plus 4 sigma are truly exceptional student, and so on and so on. So I do a Gaussian fitting on 1D marks. The same appears over here that I'm doing Gaussian fitting over the entire data in one dimensional, which is this axis. But then in reality, my data is n dimensional in nature, and a lot of people doing mathematics would know that how do we for calculate the covariance matrix of n-dimensional data. And I think there was a lecture on PCA, so you would have known how do we calculate it for n-dimensional data. So if I do x minus mu, the whole square, where this is a scalar, this is a scalar, summation under root, this is what is a standard deviation divided by n minus 1. So, but then I need to do it over n dimensions, and that is when it becomes the covariance matrix. And the covariance matrix is taken like that. So my x is probably a d cross 1 vector, my mu is a d cross 1 vector, and similarly for the other one. And this will become a d cross d covariance matrix. It's usually denoted by a sigma, which is my slide originally had. The covariance matrix is usually denoted by sigma, but then there was a summation over here, so I've taken S as the notation. Not a mathematics class, people. I'll not tell you how do we calculate the covariance matrix. And somehow this term has been given because we changed it from the standard term sigma to a S, so that people don't get confused. We call this thing as a scatter matrix. Another reason, of course, is that many people would be trying to find out the denominator n. It's not there. So, yeah, there's a difference of a constant, and that's also why we give it a slightly different term as a scatter matrix. I'm a practical person, so by all practicality of it, it is the same covariance matrix that you have heard of, and you are probably knowing about it. So that is what is my scatter matrix. But then the problem is that is scatter matrix of one class. That is a scatter matrix of one class. Let's say this is the class I. So this is the scatter matrix of class I. Now I want to minimize the scatter matrix of the class 1. I want to minimize the scatter matrix of class 2. So let's say I want to minimize S1. I also want to minimize S2. Now, again, the thing is I haven't taken the under root over here. So practically it is standard deviation square, and that will always be positive. I want to minimize scatter matrix 3. If you take S as a standard deviation, the square of it, and so on and so forth. So what do I do is, instead of saying I minimize S1, I minimize S2, I minimize S3, I minimize SC, where C is the number of classes. I say I minimize the sum of all of them because each one of them will be minimum when the sum is minimum. And that's why you see that what I've done over here is that I say it's the sum of all scatter matrices. And all, I mean all classes. So I minimize the sum of scatter matrix of all the classes, going a little bit pictorially. So I want to minimize sigma A, I want to minimize sigma B. So I say I need to minimize sigma A square plus sigma B square. Sigma is standard deviation, and over there it's scatter matrix, which is covariance, which is the square already. That's why you don't see a square. So this SW is what is called as the within class scatter matrix. Now I emphasize on this word W. The word W says that it is within class scatter matrix. So when I say the word W, I mean within class. And within is intra. But then I need to do something else as well, and this time I am very informal. So what I need to do is I want to maximize distance as well. So what I really need to do is I want to maximize this distance as well, and the problem is, how do I maximize this distance? How do I really go upon maximizing this distance? One way to say it would be simple, that okay, I want to maximize mu A minus mu B, the whole square, because people would say that it needs to be a real number. Uh, so I mean, the easiest way would say to I want to maximize mu A minus mu B, but then they can be a class 3, class 4, class 5, they can be C classes. So Shah Rukh Khan's face, Ranbir Kapoor's face, Rahul Kala's face, Narendra Modi face, and so on and so forth. So how do I do that? So what do I do is, just like I was taking scatter matrix within class, I take the scatter matrix between classes. So this is what I say is the scatter matrix between classes. So SB is, that says what is the scatter, what's the variance, but not variance intra to a class, the variance or the scatter between classes. Now, again, I don't need to tell you how to calculate standard deviation. I don't need to tell you how to calculate covariance matrix. I don't need to tell you, given some vector data, how to calculate covariance matrix. So what I'm saying is that this thing will be exactly same as PCA. I am maximizing between class scatter matrices. So instead of taking all the points that you were taking PCA, you will only take the class means. And whatever you studied in PCA, same formulas, they all apply. So, I mean, they all apply. Whatever you studied, I mean, for the PCA, they all apply. Just change mu I to xi, it will become the standard thing that you do in PCA. So, I want to maximize the between the skater. So, what I'm saying is that in PCA terminologies, what I'm saying is, instead of considering all data for PCA, I will only consider the arithmetic mean of the different classes as the data, and I will maximize variance of that data. So I'll maximize variance, I'll apply PCA, I'll do the standard PCA technique, but I'll only consider the data which is the arithmetic mean of all classes. And now my two objectives are there. So I want to maximize within class distance. I want to minimize within class scatter. I want to maximize between class scatter. And how do I do it? Let's look at the second equation first. So this needs to be maximized. So it's in the numerator. And this needs to be minimized. So it's in the denominator. And I will optimize this ratio. I say that the notation is informal because, again, to make sure that you understand that these are all D cross D matrices. So SB between class is a D cross D matrix, and SW within class is also a D cross D matrix. So don't take it like the ratio of real numbers. I would have never mentioned it as a ratio, by the way, at the first place. Now, a lot of you people would say that, okay, SB is a constant, this is the formula, and SW is constant, this is the formula. So there's no parameters that can be demised. And then again, I leave you to the person who told you about PCA. So we are optimizing that in the new coordinate axis system, and the projection in the new coordinate axis system is the one that we consider. This is what you might have looked at it before. So the data in the new coordinate axis system is a weight matrix time data in the old coordinate axis system, and in PCA and in LDN everywhere you find this weight matrix, which is also called as the projection matrix. So the PCA person would have spoken a lot about this projection matrix. So basically, when I say I'm doing it in the new coordinate axis system, so this formula where all the x's and all the mu's will get multiplied by the weight matrix W, and where the x's and the mu's will get modified by the weight matrix W, the actual formula will come out to be because x and mu both are multiplied, then it gets W transpose times W, and that's also a formula that you would have seen in the PCA probably, or you would know from the other customized distance formulas that when I do a rotation or a projection of the data, the result is what is W transpose times the distance or the matrix in the old one times W. So this is the standard thing that I have, and all that I'll do is I'll pass this as the objective of the PCA. So basically, I'll calculate this matrix, and this is the matrix that I'll give to my PCA. So a normal PCA only considers the scatter. This PCA will consider SP divided by SW. The problem is SP divided by SW is not a real number. So this is a D cross D matrix, and this is a D cross D matrix. So more formally, it's written as matrix multiplication, where the denominator becomes the mathematical inverse of cos, and the okay, this has to be SP. The numerator remains as it is. So I will just take the do the standard PCA thing. So that is what is a standard PCA. So how what do I do in PCA to calculate the weight, the projection matrix W? I take in the standard things, the eigenvalues and the eigenvectors. Eigenvalues decide how important is the eigenvector, and eigenvector is a projection that is applied to the data. So I say that with every eigenvector or with every projection, I have an eigenvalue, its relative variance, its relative importance. So I sort all the eigenvectors by the eigenvalues, and then if I want 10% of my features, I take the top 10% eigenvectors. If I want 20% features, I take the top 20% of the features. If I want 40% of the features, I take the top 40% of the eigenvectors. So I take in those values, and with the chosen eigenvectors, I just stack them up, I just concatenate them up, and that becomes my weight matrix, which is D cross the reduced dimension D dash. And therefore, if I apply any, my apologies, D dash cross D. So if I apply any data which is a D cross 1, I get a D cross D dash cross 1 vector, which is the projected matrix. So this is something that you have already looked at from the PCA side of view. My lecture will end up over this part, that the objective measure is changing into maximizing the between class scatter and minimizing the within class scatter. Now, I just thought I will give in one classic formula as well, because technically this formula is more correctly derived from this formula. So I had two classes, mu1 and mu2. So I want to maximize this distance, that is mu b minus mu a, the whole square. Don't take the square very seriously, because mu and mu b are d cross 1 vectors. And I want to minimize sigma a square. So again, don't take it as a real number, it's a covariance matrix. So this is what I should be doing I mean, this is more technically what I explained. I want to maximize the distance between the means and I want to minimize the scatter of the first matrix and the scatter of the second matrix. But then this is in the new coordinate axis system. So by introducing the projection matrix, I can project the data into an unknown plane. W is what I finally need to find out. So the mu will become W times the old mu, and mu2 will become W times the old mu. And similarly with the scatter. And if you apply some standard things that this crosses the multiplication of these two matrices, this is basically matrix multiplication. Why am I teaching you mathematics, which you already know? So you get in exactly the same formulation, which is to maximize the between class scatter and to minimize the within class scatter. Now, I'll get into two quick commentaries. My time is like 3 minutes. So, in 3 minutes, I will get into my closing remarks and the summary and a discussion that I started. So, let's end it up in another 3 minutes. So, uh, we started out with this thing that the PCA is a great tool. PCA, Principal Component Analysis, is an absolutely wonderful tool. I've used it so many times practically and not just to get publication myself. So one of the essential things that I still like to do is to visualize data at different formats, whenever it's 5 dimensional, 6 dimensional, 100 dimensions. I would like to visualize that in 2 dimensions and so on and so forth. There have been cases where I have used it as a dimensionality reduction technique as well. So sometimes you do need to get rid of the data. It's just that even though you may have a lot of data, there is no real problem in getting rid of dimensionality because every technique eventually talks about dimensionality reduction. If you are a fan of deep learning, that's what it does exactly. So the deep learning techniques also are losing dimensionality of the data as you go layer by layer and layer by layer. And if you have a nice statistical technique to reduce dimensionality, there is absolutely no problem in reducing the dimensionality that you want. So PCA is still the de facto tool when you need to lose dimensionality either for visualization perspectives as well as for the perspectives that you want to get rid of some of the features, you want to get rid of some of the data. It could be as an input to the model, it could be between the working of the model, or it could be that you are getting some latents and somehow the latents are high dimensional in the feature space, so you want to still get rid of them. Now, LDA is exactly same as PCA, except for it uses the class label as an additional information. So I do exactly the same thing as PCA. I make one very small one, very little change that I also consider the class labels. And instead of my problem being one objective to maximize variance between the data item, it becomes two objective. One of it, same as before, that I want to maximize the variance between the class means, same as PCA. But what I also want to do as a secondary objective, I want to minimize the variance, minimize the scatter, minimize the spread of data within the same class. So instead of taking just one matrix that you do in PCA, I take the division of two matrix or the inverse of the of one matrix, which is the which is the within class scatter with the second matrix, which is a normal, the scatter between the classes. And the reason why I say it's not very popular because when I visualize the data, for visualization purposes, I would not like to restrict it to artificially increasing the separability between classes to naturally see how much they are separate. When I have a raw data, so it is far from something that can be classified. I'm just looking at it, and therefore I would probably not like to use the class labels or know the class labels. When I'm doing it within the models, some people think that I don't want to bias it towards the main classes. So LDA so far has been an excellent tool, but then it's an excellent tool only for problems wherein Your inputs are of high dimension, you want to reduce dimensionality, you have the class labels. Historically, it was the best thing and the best technique possible, but then the problem became that these days you have too large data sets and you have too much of compute, and these models don't require dimensionality reduction. So if I don't require dimensionality reduction, I might not use it as well. PCA still has the use cases that I just discussed, and I think my time is up. So if there are questions, I would be happy to take that.
Okay, participants. So, do you have any doubt? Then you please ask. Is everything fine, or if you don't have any doubt, then please clear. Write in the chat box. The quiz will start at 3 o'clock and it will remain open till tonight 11:59 p.m. Okay, so
Okay,
if you
there's
don't have,
interesting
yes,
question about the speech recognition and how you can apply it. Now, the major problem with speech recognition is, I mean, that speech signals in raw are very similar to what we have in image. So, in an image, if I move the camera one step towards the right, the input looks very different. All the pixels go one step left, and same happens with speech as well. So in speech recognition, if you're applying a classic technique, you have to do the standard feature extraction. So you can use the wavelet decomposition techniques, you can use the formants, you can use all the classic feature extraction techniques that you may know, but you have to apply classic features because those features will be invariant to factors of variation, which is speaking fast and slow, speaking with a little delay, or speaking before and after. The raw input doesn't cover the factors of variations. Now, given that you have either the wavelet decomposition techniques or the formants or the spectrograph analysis features and so on and so forth, given that if you have any of the classic features that you have already extracted, you can extract more number of features and then use techniques like the LDA to lose dimensionality, and that way it would use one technique which are, I mean, which are, let's say, the Fourier coefficients or something, which in one way is extracting data, and out of the extracted data you'll have a second technique which is like the LDA, which is taking correlations between the extracted features to get the best feature combination. So it's a two-step approach: extract classic features from raw data and reduce dimensionality of the classic features by using LDA. Okay, people, I do have a meeting, so I don't think so there are any more questions anywhere. I think I will take a leave. It has been an absolute pleasure to speak to you people, and apologies for my bad writing. I'm a classic whiteboard professor. It's just that these formats don't allow me to use a whiteboard with my favorite marker and eraser. So thanks for keeping up with me despite this handicap.
Thank you, sir, for coming and accepting our invitation for a short notice in this one. So, thank you, sir, for nice presentation and giving insightful lecture of this linear discriminant analysis. And you conducted before that the two lecture before this one. So, thank you very much for taking all these lectures. And I appreciate your energy, your passion that I can see from your face. So thank you, sir. Your voice, your energy that I can feel right now. So thank you, sir. Okay, sir.